Let's dive a bit deeper. Level 3 is algorithms. OpenAI beat top pros at Dota in 2019. I consider this the top result in the field. How advanced was the algorithm used for this feat? Pause and guess. Ready? The solution was PPO and a 158 million parameter network with a 1-layer LSTM. That's a model you can run at home, and while the 1024 GPUs used to train it were a lot by 2019 standards, that's only around 1% of the scale of GPT-4. PPO was published in 2017 and is still the most widely used algorithm in RL, outside of maybe soft aftercritic in parts of robotics. Keep in mind, algorithms are academic bread and butter. There is tremendous incentive to make progress and publish here, and there have been dozens to hundreds of papers claiming to beat PPO. But none of them have caught on more generally. As you might expect from the previous section, it's a common story in RL to try out a newly published method on a different environment, only for it to significantly underperform the much simpler baseline. This is going to change with Pufferlib. Algorithmic progress is not our immediate goal, because it will soon become an inevitable byproduct. You can already run exhaustive experiments on a few environments overnight with Pufferlib. As soon as we accumulate just a few more fast environments of varying type and complexity, the pace and accuracy of evaluating methods will increase so dramatically as to virtually automate this process. But until then, PPO solves Dota and it will probably solve your problem too. Level 4 is libraries. In language and vision, most researchers just need PyTorch, a dataset, and a stack of papers to read. Reinforcement learning isn't like that. Our data comes from simulators. We'll talk about all the different tools that go into dealing with these, but for now, let's just look at off-the-shelf bundles of tools. The best known one is probably Stable Baselines 3, which makes getting something working quick for beginners. Tianshou shares a similar design, but is much less known in the US. Then there are higher perf libraries like Sample Factory and Mulib, which run like Swiss watches. Smooth and beautiful, just don't try to modify them yourself. There's also TorchLib, a newer library with quite a bit of promise. All these take some time to learn, and none of them will suit your needs in all cases. My overall pick is CleanRL, which provides short, single-file implementations of major algorithms. RL is an emerging field, and users need white box software that they can easily edit any portion of. So how does Pufferlib fit in? Our demos run on an optimized version of CleanRL with a several-fold increase in performance, but really, the core of Pufferlib is not just another training library. We instead focus on lower-level optimizations that enable efficient and general simulation. And for that, we'll have to dive deeper. This is where we start getting into major advancements exclusive to Pufferlib. Level 5 is vectorization, the process of getting data from parallel simulators running on different cores to the GPU. To illustrate just how difficult this is, LLMs with thousands of GPUs are trained on the order of tens of terabytes of data total. Our single GPU demos can consume over a terabyte of data per hour. And this is not read from disk, but gathered from over a billion interactions with hundreds to tens of thousands of parallel simulations. Nothing else matters if you can't get that data fast enough. If your vectorization caps out at 5,000 frames per second, your training caps out at 5,000 frames per second. Optimizing this process is hard because vectorization has to handle a ton of different types of simulators. To name but a few complications, some environments run at inconsistent rates, some have high bandwidth requirements, some have variable numbers of agents, and many require handling highly structured data. I rewrote this layer of the RL stack from the ground up based on my experience developing neural MMO throughout my PhD. Pufferlib vectorization can handle tens of gigabytes of data per second with virtually zero overhead from inter-process communication. You can read the full details of our architecture in the Pufferlib white paper, but as a quick summary, our biggest improvements include optimized shared memory layout, asynchronous buffering, custom signaling between processes, and multiple strategies based on an automatic profile of your environment. In more practical terms, if your environment is complex, Pufferlib will make it work where alternatives will not run. If your environment is slow, Pufferlib will make it faster than existing alternatives. And if your environment is fast, Pufferlib can scale linearly where existing methods are often slower than single thread. Level 6 is compatibility. making RL work with tons of different types of simulators. Until just a few months ago, this was the biggest bottleneck in pushing reinforcement learning to work on more interesting problems. And it was the bane of my existence developing neural MMO during my PhD. I saw many amazing RL projects fail because of it. There was just no efficient method for getting structured data from complex simulators into standard learning implementations. The solution was so obvious in retrospect, but I can confidently say it is unique to Pufferlib, because if anybody had come up with a general formulation, it would be everywhere by now. Pufferlib packs up all the data from your environment into flat buffers. Then, right before your model needs to know the structure of that data, it unpacks it. Simple, right? Well, this means that the whole vectorization, library, and algorithm layers do not need to care what your data looks like. Your simulator can be anything, and you can eliminate thousands of lines of inefficient structured data processing code from your RL infrastructure. Instead of keeping this technique a secret, I've made it available for free in Pufferlib. We're nearing the bottom now. These are the esoteric depths where discoveries are made. Level 7 is wrappers. Code that runs on top of existing environments to modify how they behave. Wrappers are pervasive. Virtually all commonly used environments have several post-processing steps, such as grayscaling or resizing frames, stacking observations together, repeating actions for multiple frames, and adding extra logging. And they're almost all unoptimized Python. This is the resize operation used in the most common wrapper for Atari. This one little interpolation right here probably accounts for a quarter of the CPU time allocated to reinforcement learning in the last decade. I rewrote it in one line, and immediately doubled the overall training speed of Atari with no performance degradation. Shortly thereafter, I found an error in another standard wrapper that prevented agents from learning multiple different games. The same day, I removed the rest of the Python wrappers and replaced them with C++, which ironically enough was already available in the base Atari package. Other common errors I see include rendering the environment at a high resolution and then downscaling, instead of rendering at a low resolution to begin with. I found this in the standard Doom package and got a several-fold speedup just by enabling an unused resolution option that was in an obscure config file. For ultra-high performance environments, the standard RL APIs provided by Jim and PettingZoo themselves are too slow, because they require processing Python dictionaries, though this really only becomes a concern above 1 million steps per second. Speaking of which, level 8 is environments, the set of existing simulations available. There are tons of interesting RL environments, but few of them are fast. In many cases, I question how it is even possible for them to be this slow. Here's the popular Crafter environment, designed in part to reduce computational requirements. It runs at 320 steps per second on a high-end desktop, and it also receives no noticeable acceleration with standard vectorization methods. It does run up to 2800 steps per second with Pufferlib, but that's still unusably slow. The reason? Atrociously optimized Python. This trend continues in several other environments, such as this racing environment, which runs at low hundreds of steps per second, and this traffic simulator, which somehow runs at dozens of steps per second. We do have some, at least reasonably fast environments that would be usable if we stopped slowing them down with bad wrappers. I've gotten Atari up to 60,000 frames per second on a desktop and ProcGen to 150K. That's still not amazing, but it's pretty good for something being rendered to pixels. Doom is reasonably fast as well, but the project would need quite some work. Some older M's are surprisingly fast, one of my favorites being NetHack, which is an 80s terminal-based dungeon crawler. It's an insanely complicated env, but I can run it at 100,000 steps per second in Pufferlib. Many environments are 10 times slower outside Pufferlib, especially with GIM or SP3 vectorization, but if you know of any others that are at least fast single-threaded, let me know. There are some newer GPU-accelerated environments, but only a few of them, like GPU Drive, Madrona's Hide and Seek, and CraftX, are complex enough to be worth mentioning. Welcome to the trenches. This is the realm of things nobody has ever even attempted. Level 9 is custom simulation. What if we replaced all the standard training environments with ones that run 1,000 times faster? That's what Puffer AI is doing right now. Atari games run at a few thousand steps per second per core. This Snake game runs at over 10 million steps per second per core. This Common Grid environment runs at 16,000 steps per second. Ours runs at over 10 million. It's not just limited to simple simulations either. This mini MOBA runs at over 1 million steps per second per core, and it has many of the elements of Dota. We have a couple more projects in the works too. So how's this possible? These simulations all run in pure C with zero dynamic memory allocations. But, provided you understand the computational requirements of RL, they don't take that long to build. Most of these are written in Python that reads like simple procedural Python. The snake and grid environments are a few hundred lines of code each, and the MOBA is currently around 1400. I did a port of the snake game to native C, but really, that was just so we could run it on our website as a demo. Try it out. All these sims are publicly available in the dev branch, and you can often find me building them live. These will be part of our next update, and I believe they will be the basis for a whole new wave of progress in reinforcement learning. Level 10 is open-endedness. For the last stop, I'd like to talk about the only problem on this list that I don't know how to solve. Building an environment in which agents can continue to learn and develop interesting solutions forever. We only have one example of what might be an open-ended system: human civilization. The original motivation for Neural MMO, the topic of my PhD, was to get as close as possible to this with a known simulation format, namely MMOs or massively multiplayer online games. I still think that this would work, and done at scale using some of the techniques I now know, could produce something an order of a magnitude more interesting than OpenAI's Dota bot. But beyond that, I don't know yet. If you have any ideas, let me know in the comments. But before we wrap up, let's look at the whole picture. The master plan of how Puffer AI will fix everything wrong with reinforcement learning. We're building fast simulators of varying types and complexities. These will replace the slow simulators and environments used in academia and in industry for testing new methods. They will not be slowed down by clunky wrappers or by compatibility issues. They will run with linear speedups across processes, fast enough to saturate even multi-GPU machines using only locally available cores. Pufferlib's simple demos already train at over 1 million steps per second and will soon scale linearly with more GPUs too. While we will not initially focus on developing new algorithms or improving sample efficiency, these improvements are inevitable byproducts of running tens of billions of steps per experiments per GPU per day. If you're in an industry working on reinforcement learning, our tools are free and open source. As of right now, you can also purchase extended support, priority features, and other services. Email jsuarez@puffer.ai or message me on X for more information. We also have special deals available for small startups. If you're in academia and would like to collaborate, let us know. Puffer AI provides free support to multiple academic labs, and we intend to expand this program in the future. And if you're just generally interested in reinforcement learning, you can follow me on X, chat with us on discord.gg/puffer, and swing by the dev streams to see many of these tools being built live. Thank you for your interest, and don't forget to feed the puffer.